In this video, I want to take a look at linear transformations from R1 to R1. And yeah, I feel very passionately about this, so um, I apologize in advance if I get carried away. Here we go. There's a theorem from the previous video. A transformation T from Rn to Rm is a matrix transformation if and only if it's a linear transformation. I want to look specifically at what happens when your n and m are both equal to 1. So we're looking at transformations from R1 to R1. Well, transformations from R1 to R1 are just functions. You take a real number as an input and you get a real number as an output. Now, granted, we're thinking of them as vectors, so you think of them as lists of one number. What's the difference between a list of one number and just having one number, right? It's whatever. So we're talking functions here. And how many times have I seen students do this? They look at something like the square root of x squared plus 9 and they replace it with an x plus 3 because they think the square root has the additivity property, although they don't say that. It's like distributive property, right? That take the square root of x squared and take the square root of 9, you have the results, right? So you get x plus 3. I did a talk at a conference, last year or so, that I called the unforgivable algebra curses, sort of equating them to the Harry Potter world of the unforgivable curses. There's Imperio, right? The Imperious curse. There's Crucio, the Cruciatus curse, and there's Avada Kedavra, the killing curse. And this one is equivalent to the killing curse. This is the worst. This is just, it should never happen. Students do it all the time. They take a plus b squared and they replace it with a squared plus b squared because they think that, everything has the additivity property. Sine of a plus b. They replace it with sine a plus sine b. Just pick a function, any function. There's a student that has said that it has the additivity property, that essentially the function distributes over addition, which when I have a face-to-face class and I can sit down and actually look my students in the eye and say, give me an example of a function that actually does satisfy this property, that f of x plus y is f of x plus f of y. Can you find one? And they'll, exponential functions? No, not exponential functions. Log functions? No, not log functions. And eventually one will say, how about if we just multiply by a constant? Like k times x. And it's like, yes, that one actually does work, right? If I do k times x plus y, that's k times x plus k times y. That's the distributive property. Good, that one works. Any others? Well, according to this theorem up here, the only transformations from R1 to R1 are, the only linear transformations are matrix transformations, which means you have to multiply your input by a 1 by 1 matrix, which is essentially just multiplying it by a number. So the answer is, well, the theorem actually says it's a linear transformation, which means not only does it satisfy the additivity property, but it also has to satisfy the homogeneity property as well. If it satisfies both of those, then it has to be just multiplying by a constant. So if you get nothing else out of this video, then take this, right? And I've said this in the past. If the graph of the function you're looking at is not a straight line through the origin, then it is not the case that f of x plus y equals f of x plus f of y. They're not equal. You can't do it, right? None of these up here, none of them work. Okay, so if that's all you get, fine, go away. But if you want to stick around for a little bit, I'm going to explain how that statement isn't entirely true. That there are other functions, but I doubt that you will ever use one in your life. For all the functions you ever see, if it's not a straight line through the origin, if the graph's not a straight line through the origin, then it doesn't satisfy the additivity property. But here we go. Here's my theorem. If V is a one-dimensional space, and you've got a transformation from V to some other vector space that satisfies the homogeneity property, then it also satisfies the additivity property. That is, for your domain space being one-dimensional, homogeneity implies additivity. And here's my proof. The proof. Well, if it's a one-dimensional space, it has a basis with one element in it. So let V, the little vector V here, be the basis for the vector space capital V. And let U and W be any two vectors in the vector space V. Well, because this is a basis, I know that U can be written as K1 times V, and right, I take a linear combination of things in the basis, but since there's only one thing in the basis, the linear combination means just a scalar multiple of. And likewise, W is some other constant times V. So I got K1 times V is U, and K2 times V is W. Now, consider the following. I want to know what is T of U plus V. I want to show that it has the additivity property. So I want to show that T of U plus V is equal to T of U plus T of V. So let's see how that works. Well, T of U plus U plus W, here, U plus W, is, I'm going to replace U by K1V, and I'm going to replace W by K2V, which is what they are. Okay. Now, inside the parentheses there, we are talking about addition in vector space V, which is one-dimensional, which is why we could do that. But now there's a distributive property in V. V is a vector space. So I can factor out this vector V right there. And so I got in parentheses K1 plus K2 times V, and I'm taking the transformation of all that. But I'm assuming that that transformation has the homogeneity property. So this constant now, K1 plus K2, can come out in front. It's K1 plus K2 times T of V. But now on the outside here, I'm looking at vector operations in W, and there is a distributive property in W. So I can take this vector, T of V, and multiply it in to both of those constants. So I got K1 times T of V plus K2 times T of V. And, oops, I have now, again, the homogeneity property that I'm assuming that the transformation T has. So the K1 can be pulled in here, and the K2 can be pulled in there. And so now I have T of K1V plus T of K2V, but K1V is U, and K2V is W. And so T of U plus W is T of U plus T of W, and my theorem is proven. Okay. So when your domain space is one-dimensional, if you know homogeneity, you know you have additivity. Now, how about the other way around? Are these two equivalent? If I know additivity, can I get homogeneity? Let's try it. Well, let's see. Let's start with, let's just scroll. Let's go all the way here. So I'm assuming now that T has the additivity property, and I'm trying to show, does it have homogeneity? Well, if I take T of 2 times a vector, then that would just be T times that vector plus itself, V plus V. And if it has additivity, then I know that that's equal to T of V plus T of V, but that's just 2 times T of V. So it looks like T of 2V is 2 times T of V. Good. How about I could do it with 3 and break this in, so 3V, so V plus V, and split that up and end up with this. So it actually turns out for any integer n, I can show that T of n times V is n times T of V. Now this doesn't prove homogeneity yet, because homogeneity is for all real numbers. It works. So all I've done so far is all the integers. But also notice I could do something like this. T of V is T of a half V plus a half V. That is, I'm just taking the V in parentheses and writing it as a half of it plus a half of it. Okay. But then if I've got additivity for this transformation, then that's T of a half V plus T of a half V, which is 2 times T of a half V. And then if I say this first thing is equal to the last thing and divide both by 2, I get that T of a half V is a half of this thing. It's a half times T of V. And it looks like the half can be pulled out, as it should with homogeneity. Likewise, I could do the same thing with any integer. I could show that T of 1 over n times V is 1 over n times T of V. And with a combination of both of those ideas, I can actually show that for any rational number, P over Q, we have that T of P over Q times V is Q over P times T of V, which, try to say that 10 times fast, is the homogeneity property as long as I'm multiplying by a rational number, which there's an awful lot of rational numbers. And they fill up they fill up a lot of the line, not really most, but But it misses all the irrational numbers. And so is it true then for irrational numbers as well? But if k is irrational, it turns out I don't know anything about t of v. And here's a picture, at least the starting of a picture of a graph of a function. So what I've done is I've assigned t of 1 to equal 1. So there's a little blue dot right there. Now, according to what I did up above, is that any rational multiple of 1, the homogeneity property is true. And so there's t of a half, and t of a third, and t of a quarter, and all these dots along this line right here. This happens to be the line y equals x, right? Because I assigned 1 to 1 and a half to a half. All of these points are for inputs that are have denominators of 10 or less. So all of the half and all of the thirds and all the fourths and the fifths and the sixths and the sevenths and the eighths and the ninths and the tenths. So those are those. Right? Of course, there's many more rational numbers in there with bigger denominators, but these are the ones with the small denominators. Okay. So the line y equals x should be the line of the graph of this function, right? If the homogeneity property was true, and I assigned the value of t of 1 is 1, everything else should be determined. However, it works to do this, the following. The dot right here is corresponding to the square root of 2, which is about 1.414, right? It is not a rational multiple of 1. It is the square root of 2 times 1. Right? And so rather than being, if homogeneity really worked, then the point at the square root of 2 should have a height of the square root of 2. But what I'm going to do is I'm going to say, no, I want the function value here to be 0. And so then a half times the square root of 2 is also at 0. Well, half times 0, which is 0. And then a quarter, and all of these dots, little blue dots down on this axis, are rational multiples of radical 2, where the rational multiple has a denominator of 10 or less. Okay. And then what you see up here are all of the linear combinations of those things. So if I did radical 2 plus a tenth, that would get me over to here. And the function value should be, because additivity works, it should be the function value of radical 2 plus the function value at a tenth. Well, the function value of radical 2 is 0, and the function value at a tenth is a tenth. So at this point right here, there's the function value. And then radical 2 plus a half, radical 2 plus 1 gets me up to here. And all of these points are the function value at some linear combination, some rational linear combination of 1 and the square root of 2. Okay. But then there's like, the square root of 3. And so what I have here is a graph with radical 2 and radical 3. Radical 3 is 1.732-ish. And so there's a little green dot right here at the square root of 3. I still have the dot for radical 2 right there. And so now the green grid is all the rational multiples of 1 and the square root of 3. But also I should do the rational multiples of radical 3 and radical 2, which would be a whole bunch of other dots. Or then you could even throw in other points. The red ones are, I threw in the golden ratio, 1.618 something, right? And the red dots in there are the rational multiples, rational linear combinations of 1 and that number. But then I should do also that this becomes immensely dense and completely discontinuous everywhere, right? It's possible for every irrational number to assign a different function value and then just do all the rational multiples of that. And you get these really crazy graphs that are just completely dense in the plane. And they satisfy the additivity property, but not the homogeneity property. So I'll admit I have lied to students saying that if the graph is not a straight line, then you don't have additivity. Which is true for the functions that you will ever deal with, because you will probably never deal with one of these.